Welcome to part 2 of ionic bonding. We're going to start where we left off on part 1. Now we go into the why of everything, which you don't need to know if you're only doing foundation. So why do ionic compounds have such high melting and boiling points? Now the reason for the high melting and boiling points is down to this, the lattice structure that we talked about a minute ago. This is only one very small segment of a giant lattice. There will often be thousands of ions in that lattice structure. Now if we think about all those electrostatic forces that have to be overcome to split that lattice structure up, that explains why we have high melting and boiling points. To overcome those electrostatic forces, we need lots and lots of energy, which comes from that heat to break it up. Now thinking about why our ionic compounds only conduct electricity when molten or when dissolved, but not when solid. Here we have a beaker with water molecules in. Now, water actually does not conduct electricity. It's a very common misconception. It will only conduct electricity when there's other stuff mixed in. That's why in science labs you will often use distilled water. It means it's pure water, it doesn't have any impurities, and therefore if you were to test it, it would not conduct electricity. Now I've got a picture of the lattice structure in the top left hand corner of the screen. Now I'm not going to use the colours associated with the lattice structure, I'm going to use the original colours that we talked about for sodium and chlorine at the start. So red is going to represent sodium ions, and blue is going to represent chlorine ions. That diagram in the corner is just to remind you what the lattice looks like. Now, some ionic compounds will dissolve in water, some will not. You will need to know those solubility rules, and we'll talk about that in a second. So if something dissolves, it's soluble. If it does not dissolve, it's insoluble. You need to know what those definitions mean. So if you've ever played an April Fool's joke where you've put salt in someone's drink, you will know that salt, as in sodium chloride, will dissolve in water. You do not need to know why it will dissolve in water, you just need to know that some can and some cannot. If you want to know why water can be used to dissolve some ionic compounds, you could ask your chemistry teacher. It is covered in A-level chemistry though, so it is beyond GCSE. Now our beaker has water in, it also has our table salt in, our sodium chloride. Now we need to bear in mind that those positive and negative charges are no longer together counteracting each other out. They have been separated. Now for something to conduct electricity, it must contain charged particles, but those particles also need to be able to move, which is why only metals can conduct electricity when solid. However, when molten, so in its liquid state, or when dissolved in water like this, we have charged particles that are able to move. In the lattice structure, they can only vibrate, they cannot move around. That means that when they're molten or when they're dissolved, our ionic compounds can conduct electricity. Now the Edexcel exam board requires that you learn the solubility rules. So it requires that you learn what does dissolve in water, so what is soluble, and what doesn't dissolve in water, so what is insoluble. You need to learn these. They can be found on page 132 of the Edexcel Additional Science textbook. Now one other important thing about soluble and insoluble substances are precipitates. A precipitate is formed from two soluble reactants reacting together to form an insoluble product. This is where our state symbols come in. Now we have different state symbols. S stands for solid, L stands for liquid, although we tend to only see this when talking about water or talking about molten metals. AQ stands for aqueous, which is when something is dissolved in water. This is the one that we see most commonly. And another one is gas, G. So the state symbols we would see in a precipitation reaction would be aqueous plus aqueous reacts to give an aqueous substance plus a solid substance. Okay, so in this example here, we have lead nitrate and we have potassium iodide reacting together to form potassium nitrate and lead iodide, where the lead iodide is solid, and that is our precipitate in this precipitation reaction. Now, one thing that is commonly asked as a 6-mark question is how to get a dry sample of the precipitate, which in this case would be our lead iodide. So we would need to mix these two reactants together in a suitable container. We would then have our aqueous product and our solid product together. We would then have to separate these. Now, one easy way to separate them is to use a filtration system. So we would filter our lead iodide and our potassium nitrate through some filter paper and a funnel. We would collect the potassium nitrate and dispose of it. We would then be left with our lead iodide in our filter paper. Now, it does often ask for a dry sample in the question. Now, one thing is, when we filtered it, we cannot guarantee that all of this potassium nitrate has been removed from this lead iodide, as it's still wet. Now, one way to make sure that is the case and it has been fully removed is to wash this lead iodide with distilled water. That will remove any of these potassium nitrate ions and leave us with only lead iodide. We can then stick the filter paper with the lead iodide into an oven to dry. Now, when it comes to naming precipitates, it's quite straightforward, although people often make a mess out of it. If we break it down to A, B and C, D reacting together, we would then see the products AD plus CB. The first part of the name stays the same. The second part of the name swaps over. So, for example, if we go back to our lead nitrate plus potassium iodide, lead would be our A and our nitrate would be our B. The potassium would be our C and the iodide would be our D. Now, our products are lead iodide, so that's our A and our D, and our other product is our potassium nitrate. So potassium was our C, nitrate was our B. So the ends of the two reactants have swapped over to form new names for our two products. Something else you need to know about as part of the course is barium meals. So barium sulfate is given to patients to help diagnose problems with their intestines. So when you have an X-ray, the X-rays cannot pass through bone. It's opaque on an X-ray. Barium sulfate is the same. It appears opaque on an X-ray. That means the X-rays are absorbed. This allows a doctor to see if there are any blockages anywhere in the intestines. The barium sulfate is presented to a patient as a barium meal, so they drink it. Now, most barium salts are toxic. However, barium sulfate is insoluble. That means it cannot go into the bloodstream. It passes straight through a patient's digestive system as a solid. This makes it safe for its use in medicine. Okay, now last bit, I appreciate this has gone on quite a while now, is testing for ions. So we need to be able to test for cations, which are positive ions, and anions, which are negative ions. Now, one way I remember the difference is to picture a cat. Now, I apologise for my drawing, it is terrible, but I draw a little plus in its nose. That reminds me that positive ions are cations, and then I remember that anions are the opposite, they're negative. So firstly, we're going to be testing for our cations. Now, all our metal ions are positive. That means that all our metal ions are cations. For cations, we want to conduct a flame test. Now, you've probably done this in your practical science lessons, but there will be 4 key substances that you need to know and that you need to remember what colours are produced. You need to know that sodium will turn yellow in a flame test, potassium will turn lilac, calcium will turn red, and copper 2 ions will turn green-blue. Okay, so another high marking question in the exam is often asking how a flame test is conducted. So we start off with a wire loop, which we have to dip in acid, often hydrochloric, and then hold it at the edge of a Bunsen burner flame. That flame has to be on a blue flame, not a yellow flame. If that flame changes colour, we then repeat that until there is no colour, meaning our loop is clean. We then dip our clean flame test loop into our sample, which can be solid or it can be liquid. We would then hold the loop at the edge of the Bunsen burner flame and see if there's a flame colour. And then we can repeat that with different samples to see what cations each sample contains. Flame tests have been extremely important over time, and they've led to the discovery of new elements. Flame testing is a type of spectroscopy, and this has been used to discover elements such as cesium. Now, obviously, if you're just testing something, it might have multiple cations in it. So we can use a prism to separate out the colours produced. If there's a new colour we haven't seen before, it could be a new element, which is what happened in the case of cesium, and then a year later, rubidium. Now looking at anion tests, there are 3 tests that we need to learn. We need to learn how we can test for chloride ions, sulfate ions, and carbonate ions. So in the test for chloride ions, we start off with adding a few drops of dilute nitric acid. We would then shake that solution. We would then add a few drops of silver nitrate. And if it's a positive test, it will form a white precipitate, for which I've put PPT here for short. To test for sulfate ions, we would add a few drops of dilute hydrochloric acid, and we then shake it. We then add a few drops of barium chloride, which will form a white precipitate if the test is positive. Now, if we react a carbonate with hydrochloric acid, we would expect to see carbon dioxide given off. That means we should see bubbles. One way to be sure that the bubbles given off are carbon dioxide, and therefore proving we have a carbonate, is to bubble the gas through lime water. If the lime water turns milky, we have a positive result.